Okay, so I will talk about complexity results.
It's an unstable.
I have to write fast. And this is about definable equivalence relations. So I will start with an introduction to definable equivalence relations. And yeah, so recently my PhD student Balázs pointed out that the difference between research math and teaching is that in teaching you tell the same ideas over and over again to different people, while in research math you tell the same ideas over and over again to the same people. So apologies if you have seen all this. Also, if you have any questions, just feel free to interrupt me. Okay. So first the introduction about definable equivalence relations. So the motivating question is maybe very naive, is that are there more groups up to are there more countable groups up to isomorphism than real numbers? Than the real numbers. Yeah, and of course the answer is no. I mean, both of these sets have the same cardinality C. But somehow the moral of descriptive set theory or Borel combinatorics is that oftentimes if you don't ignore the definable information, you gain interesting math. So you gain interesting information if you look at the definable content of some statements, and yeah. So what would be the definable? It's very important. They actually do know that there are more countable groups. So let's see. So of course, the two sets have the same cardinality. But on the other hand, if you want to witness this constructively, so what does that mean? It means that to a given countable group, you want to associate a real number so that two countable groups are isomorphic if and only if the real numbers are the same. So in other words, you want to characterize isomorphism of groups by invariance. And groups form a nice space. Reals also is a nice space, so you can ask whether you can do it, say, in a Borel way, in some constructive way. And it's not hard to see that this is not possible. So in some sense, yes, there are more countable groups than real numbers. Yes, definably. Okay, and in this sense you can treat, okay, so there was this equivalence relation of isomorphism of countable groups, and in this sense you can think about it as some sort of definable cardinality. And we like cardinalities, or we like cardinals, we want to compare them. So it should be a sufficient motivation to consider equivalence relations or definable equivalence relations with some natural notion of reduction, and this is what I've just described. So if you have two equivalent elements, you want to send them to equivalent elements and inequivalent elements to inequivalent elements. So let's write down the most important definition. So assume E is, and I will only consider Borel equivalence relations. E and F are Borel equivalence relations. On, say, standard Borel spaces. y, and we say that E Borel reduces to F, so E Borel reduces to F. If there exists an F map X from Y, Borel, with the property that if I take two elements from X, I have that they are E equivalent if and only if their E F image is F equivalent. Okay? So this, I mean, you can see that this is what exactly happened, or what exactly doesn't happen in the case of Borel, of isomorphism of groups. Okay, and maybe I will have to make some strategic decisions. So, okay, you can ask, how does the hierarchy look like? And well, in the beginning, it's completely trivial. So it starts with equality on the one element set. And then it, of course, Borel reduces to equality on the two element set. And this is also an initial segment. What does that mean? It means that if you are an equivalence relation which does not reduce to the equality on a one element set, then this means that you have at least two equivalence classes. In other words, you reduce this guy, the equality on two element set. So it starts like this. This is an initial segment, and it continues like this. Equality on three element sets, da da da. And everything here so far is obvious. I get to equality on the natural numbers. And then the next step is that it continues as, okay, it continues this way. So it keeps being an initial segment. So what does this mean? It means that if you do not reduce to equality on the natural numbers, then you must reduce equality on the Cantor space. And this is already a non-trivial theorem. This is Silver's dichotomy. Okay? But so far everything is so good. I mean, this is what we want from cardinalities, right? That they are nice, linearly ordered, and they have some initial segments. What happens then is the famous E0 dichotomy. So it keeps on being an initial segment, it keeps on being linear, and this is sometimes called E0 dichotomy, sometimes. The original version was proved in the 60s by Guillaume and Efros, I think independently, and then the more general version for for Borel equivalence relations was proved by Kechris. And is it Jackson? Harrington, okay. So I remember that it's before Kechris, Harrington. Okay, good. And okay, so what is this equivalence relation? This is the definition of E0 is that two reals. This is an equivalence relation on the Cantor space, and two of them are equivalent if and only if they are the same after a while. So X and Y are on the Cantor space, are element of the Cantor space, and for there exists some K such that for all K prime greater than or equal to K, you have Xk prime equals Yk prime. Okay? All right. And sort of the question, what happens after E0? This is the main ideological question for this talk, and I guess in general. And it turns out that it gets crazy. It gets very complicated above E0. So it's not linear anymore, and we know a bunch of fantastic results that what happens above E0, but we also do not know a lot of things, maybe much more things than what we know. For example, there is a direct successor. This is also a famous result by Kekris and Louveau, E0, but we all know that there are other right successors which are incomparable. So somehow, I mean, let's say that this is a big question mark. It's a very complicated structure, and there are very basic open questions left open. And in this talk, I will only consider countable Borel equivalence relations. This is sort of a famously misleading terminology, especially after equality on the natural numbers. So, and Borel equivalence relation is countable if every class is countable. So E is called countable if every class is countable. And I will abbreviate them by Siebers, countable Borel equivalence relations. And I will be interested in the structure of Siebers above E0. Okay, so maybe I make another picture. So here is E0, and here is E0. And here, this is the blob of Siebers. Okay? Now, let me introduce just some terminology to be able to talk about these things. We call a Sieber E is called hyperfinite. If E is Borel reducible to E0. Okay? So if it's below E0. Okay, this is like the most important notion for us, and if you only remember one thing, then this should be it. Okay, and okay, so why is the name? This definition sort of doesn't explain the name. Well, the next proposition does. So the following are equivalent for Siebers. First of all, E is hyperfinite. And E is the increasing union of equivalence relations with finite classes. So this is important that it's increasing. And Fn's should be Siebers with finite classes. So finite Siebers. Okay, and this should explain the name of hyperfiniteness. It can be somehow very well approximated with finite equivalence relations. Okay, and the third characterization, third equivalent thing is that, and it already connects this whole thing to group theory, is that E arises as the orbit equivalence relation. Of a Borel action. Of the group Z of the integers. I'm not going to define orbit equivalence relation. It's not super important. You should at least visualize this, and people like to visualize it as you have this equivalence relation E. There are these classes. So these are the classes of the equivalence relation, and this group Z can move everybody around sort of in the class in a nice manner. So there are lines in these classes. You can sort of line them. Okay? And this is a well-known equivalence, and I guess we should think about hyperfinite equivalence relations as simultaneously as these things. And I guess the most basic question here about Siebers, and I think it was not clear already in the beginning for some time, whether this blob collapses, right? Are there non-hyperfinite Siebers at all, right? And it turns out that there are. In fact, there is a very rich structure. So the first statement is by Slayman and Steele from the 80s, and they proved that there is an equivalence relation, a countable Borel equivalence relation, which is not hyperfinite. Okay, so maybe. But won't it fall down? We'll see. Okay, so this is the first theorem, Slayman and Steele. Steele, I think from 88, showing that an equivalence relation called EF2 to the F2 is not hyperfinite. Okay, and in fact it's in the top here. Okay, so F2 here is the free group on two generators, and okay, so how does this proof go? Well, I mean the free group. What is different from what is the meaningful difference between the free group on two generators and Z? Well, the free group on two generators is not amenable, and Z is, and you want to do a dynamical version of this proof, and this is what they have done, and actually. Of course, here you have to use some, in infinite case, you have to use some sort of additional thing where you want to do these dynamical versions, and otherwise you get into this purely axiom of choice context where everything trivializes. So the proof uses measure theory. Plus non-amenability. Of F2. Okay. Some further results. Okay, so first, next question probably, okay, there is somebody here, there is somebody here. Is there anybody in between? Is it maybe still linear, this ordering? And maybe a very nice result by Adams and Kekris, giving significant amount of information. And I think it's from the year 2000. Yes. There are continuum many pairwise incomparable Siebers. Okay, so what the Kekris-Adams result gives that, okay, so there is something like this here. And also this is proved using some non-trivial results from group theory, from measured group theory. So again, the proof is measure theoretic. Okay? And probably the strongest result about, in general, this structure, what we have so far is this very nice paper of Clinton Conley and Ben Miller from 17, which says that actually, if you, I mean, the typical question here which you want to ask, okay, is there some nice structure here? Can you do something down below, right above E0? Is there, say, a basis? Maybe there are like 5 elements here, so that everybody else above is above of these 5 elements. And they proved that this is not going to be the case. There are the minimal basis for non-hyperfinite Siebers has the size continuum. Excellent question. It's open. So I mean, the moral of the story is going to be that this is very complicated. We don't know anything about it. Right? So again, and then you can guess, okay, so how this is proved? Well, it's an annals paper, so I won't be able to finish it in one line, but this also uses measure theory. Okay, so all right, so what can we say? I guess we can formulate at least this question which bothers us. What happens above, so this is what happens above G0, sorry, E0, what happens above E0, and one way of formulating it, at least this kind of intuition, that everything is measure theoretic. Yes? But this follows. I mean, they prove that even with measure reducibility, that minimal basis has the size continuum, right?
Well, I mean, you might have something which is it's measure hyperfinite, it's not hyperfinite. But it's still like...
All right. Yeah. Yeah. So it's definitely a measure. Yeah. So I guess it still could be. Okay. So in the measure theoretic context, you're perfectly right. Just the minimal basis for non-hyperfinite Siebers in the measure theoretic context. Thank you. I wanted to squeeze too much of it. I will define the sort of the measure theoretic context, or at least some part of the measure theoretic context here. Okay, so so I guess there are very basic open questions which are not known here, and somehow we have this definition which sort of makes precise, in some sense, the intuition that everything is measure theoretic about E0. Well, first of all, okay, so what does measure theoretic mean here? Intuitively, measure theoretic should mean that you can always ignore a measure zero subset when you want to solve something. So let's say that E is measure hyperfinite. Say mu hyperfinite if for all mu measures, Borel probability measures, there exists a D Borel set. There exists a D Borel set such that the measure of D is 1 and E restricted to D is hyperfinite. Okay? Okay, and so measure hyperfinite equivalence relations live somewhere here. And I think the second most important open question in the area, basically, is the following. So maybe I will write second. Is it true that measure hyperfinite equivalence relations are just the same as hyperfinite equivalence relations? So this is a question going back to Cohn, Feldman, and Weiss, and also, I mean, this definitely appeared in the Arti-Jackson-Kekris, I think about 30 years ago. I guess in some sense the first most important question, and this is the second most important, is interesting because it has implications. It would have implications for the first most important question, or definitely if it's not the most important, but a very significant amount of effort has been going in to proving this statement, is the question of Weiss. So we have seen that hyperfinite equivalence relations arise as Z actions. Now you can, and Z is amenable, so now you can ask about actions of amenable groups. Are they always hyperfinite? And this is what Weiss asked. Is every Borel action of an amenable group hyperfinite? Okay, so there are, again, this is known in the measure theoretic context, so actions of amenable groups live something like here. Of amenable. Okay. And maybe some also important question, maybe it is more ad hoc in some sense than the first two, but it's super annoying, and it has been again open since the Darty-Jackson-Kekris paper. I mean, you have this thing that hyperfinite equivalence relations are increasing unions of finite equivalence relations. Now you can ask what happens if you take increasing unions of hyperfinite equivalence relations. So are they hyperfinite? That hyper-hyperfinite equivalence relations and are hyperfinite. Okay, so what is hyper-hyperfinite? This is, so is hyperfinite if it's the increasing union of hyperfinite equivalence relations. Okay, I mean, this should be an exercise, right? If you think about it, this is like, I don't know, n squared, and then the square of the natural numbers is countable or something. Of course, like, I don't know, go diagonally or zigzagging, and that is going to be easy. But this is still open. And maybe, okay, so maybe the fourth question for me is the following. Like, everything here seems to be complicated intuitively. Then, can you formalize that this is complicated? And fortunately, in descriptive set theory, we can formalize that something is complicated. So, are hyperfinite Siebers complicated? So what does that mean? In this context, it will mean that they form a sigma 1, 2 complete set. Sigma 1, 2 is sort of the natural upper bound, and sigma 1, 2 completeness would be a formalization that some sort of characterizations are not possible. If you don't know what that is, it doesn't really matter. Believe me that this is the natural definition for being complicated. Okay, and so there are all these questions, there are all these classes, and in some sense there are two worldviews. And one of them is that everything is in order, everything is nice, everything is simple, and the other is that everything is chaotic and complicated. Any questions up to this point, by the way? Yes?
You change the reducibility, but keep it effective. The basis term, but if you have two hyperfinite Borel equivalent relations, and one's reducible to another by projective function, that must be reducible by...
That is an excellent question. I mean, typically, it could be the situation, actually, I conjecture that this is the situation that under, say, projective determinacy, you have a nicer structure, and even if there is no single element basis, there could be somehow a very nicely describable basis. This, I mean, these sort of sigma 1-2 complete results are very sensitive to changing the notion of Borel reduction.
You take like the Adams-Kekris example, those are not pairwise or reducible by any effect.
That's true. That's true. So I mean, but they are sort of high above. The question is, in some sense, what happens here, and all these measure theoretic results are robust. They are much more robust than just requiring Borel reduction. So in some sense, establishing this, at least it would be a very significant barrier for Borel things. It wouldn't be a very significant barrier for in general projective things. I mean, I don't know. Yeah, so I think it's not at all clear. Yeah, so. That is also not clear. That is also not clear. My guess would be that it's. I mean, my guess that it would be still a different class. But I mean, I have some personal reasons for this guess. Not very rational, I would say. Yeah, it's all open. I mean, something is that maybe I should mention that these sigma 1-2 completeness results come from characterizing the chromatic number, the Borel chromatic number of some graphs. And it seems that there it's impossible to characterize in this sense, is sigma 1-2 complete. But once you relax to projective, it seems that there will be much nicer basis theorems. So maybe this suggests that here the answer is going to be positive as well. Okay, so. Okay, so there are these two worldviews of order and chaos. So the order worldview says that everything collapses, all classes. Maybe I should draw here hyper-hyperfinite. So this is hyperfinite square. Okay. So all classes collapse. Wise question is yes. The answer to wise question is yes. And hyperfiniteness is pi 1, 1. Okay? And the alternative worldview is that everything is complicated. So no classes are the same. And hyperfiniteness is sigma 1-2 complete. Okay? So in some sense, yeah, I mean, these are a lot of statements, right? And then, I mean, I don't want to suggest that these statements are sort of pairwise equivalent. In fact, this is going to be somehow the main result. I think people consider these statements sort of equally hard. But apart from more or less straightforward implications, I think nothing was known. So for example, okay, so one straightforward implication is that if measure hyperfinite is the same as hyperfinite, then hyperfiniteness is pi 1, 1. Then actions of amenable groups are all hyperfinite, etc. So there are all these straightforward implications, but apart from them, I think nothing was known. And let's see. And our main result is that there is at least one non-trivial implication. Actually, I promised 2 complexity results, but maybe it's going to be just 1. So the theorem, it's a joint work with Josh Frisch and Fortescinco. And well, we're still working on it. I mean, the basic result is on arXiv. You can check it out. So the statement is that if hyper-hyperfiniteness is not the same as hyperfiniteness, then hyperfiniteness is sigma 1, 2 complete. Okay? So the negation of 3 implies a positive answer to 4. This is, in some interpretation, it's a weird result, and to be honest, it's somewhat still mysterious to me. So maybe, of course, the answer is that this is true, and I mean, they are equal, and this is not a very interesting result. But I don't know. I mean, I would be happy to see that also. And it seems to be the case that there is sort of a non-trivial class of equivalence relations, assuming that they are non-hyperfinite, you will get automatically sigma 1, 2 completeness results. Okay. Yes. Yes. So this is yeah. So this is sort of a faithful picture in some sense. Like in measure context, if measure hyperfinite is just hyperfinite, then everything here is just 1 point. Okay, and cool. Okay, so this result is based on an earlier complexity result with Stevo, which I'm guilty of not advertising in the right way, I think. So let's try to advertise it in the right way. It was already proven there, but somehow we can formulate a black box, and then this should be used. This could be used in a very general context, and this is what happened here. So first, let's recall that if you take a subset of the Baire space, it's non-dominating. I mean, probably this is the best audience for not to define this notion, but in any case, is non-dominating if there exists a function f in the natural numbers such that for all elements of D, G is infinitely often below f. Okay? And sort of the theorem, the black box theorem, and I will state it for hyperfinite equivalence relations, is the following. Assume that you have a C-bar that E is a C-bar on n to the n with 2 properties. E itself is not hyperfinite. And the second property is that on non-dominating sets, it is hyperfinite. Is hyperfinite on all Borel non-dominating. D. Okay, so these are the conditions. E itself shouldn't be hyperfinite, but on relatively large sets, it should be hyperfinite. And the conclusion is that then hyperfiniteness is sigma 1, 2 complete. Is sigma 1, 2 complete. Yeah, I should have attributed this to Stevo and myself, but it's too far now. Yes, so by the way, let me remark that if you want to prove that something is sigma 1, 2 complete, you should take a look at this paper, because it's actually a black box. I mean, it doesn't have to do anything with hyperfiniteness. Basically, what happens is that if you cannot solve some Borel question on the whole space, but you can solve it on non-dominating sets, then very often you get an automatic sigma 1, 2 completeness result. Okay, and a corollary of this, and maybe a corollary of a slightly modified version of this is the following. And I think this is somehow the useful way of thinking about this result. So corollary, assume that E is a non-hyperfinite Sieber, and that there is a Borel map which maps functions in the Baire space to sub-equivalence relations. I will leave it to you to define what Borel means here. So it maps functions to sub-equivalence relations of E, with the property that for each f, the equivalence relation EF is hyperfinite. I mean, so far this property is very easy to achieve. I associate to every f the equality equivalence relation. But the important property is that for any pair in the equivalence relation, if I consider those f's for which E is not in EF, then this is sigma compact. Okay, then hyperfiniteness is sigma 1, 2 complete. I will try to. Yes. 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 Okay. So what does this say? Okay. So my worldview about this result is the following: you sort of have a process. You have a process which is parameterized by a sequence of numbers. This is f. And this process always yields you a hyperfinite sub-equivalence relation of f. And the requirement is that if I take any edge, those parameter sets for which I fail to include the edge inside this equivalence relation are small. So sort of for most of the functions, you get it right for each edge. And then it again implies that it's sigma 1, 2 complete. And from this, I can basically maybe hand wave something about the proof of the main result. It's relatively straightforward once you realize that this is what you have to use. So what happens is that, okay, so what are we proving? We want to prove this corollary. Using this corollary, we want to prove that if there is an E which is hyper-hyperfinite but not hyperfinite, then hyperfiniteness is sigma 1, 2 complete. Okay, and then what is the strategy? Well, if E is hyper-hyperfinite, it means that it can be expressed as an increasing union of hyperfinite things. And now I have to describe you the process, how I create these EFs. And well, I do it in a natural way. So I start, I have to a bare tree, I have to associate these EFs. So first what happens is that I take E0. This is the first equivalence relation. This can be expressed as an increasing union of finite equivalence relations. Okay, good. Then I take any finite equivalence relation here, I factor out with it, and I look at E1. This is, on this factor, it's still a hyperfinite equivalence relation. This is a somewhat non-trivial fact. And then I do the same. So these are sort of the finite decomposition here, etc. I do the same, and I do the same again. Okay, and to each f, I sort of associate a branch of what finite equivalence relations should I take, what finite super equivalence relations should I take, etc. And sort of ingrained in this process is that the resulting equivalence relation along one branch is going to be hyperfinite. And if the original equivalence relation is not hyperfinite, then we are, at least in this situation, and it's really easy to check that for every edge, if you go further enough, so there are only sigma compactly many choices which you can make to ruin that edge. Okay? So yeah, so that's it. Let me just say the second result. The second result is as establishing another class here, which is the Borel amenable triable equivalence relations. And this is based on the idea of Andrea and Piotr Naryshkin, and this is a joint work with him, that if Borel amenable triable equivalence relations again are not hyperfinite, then you have automatically a complexity for hyperfiniteness. Okay, so I guess this points towards asking, okay, what classes have this property? For example, Sue asked this question for so-called z-square orderable equivalence relations. I think that is also a very good candidate to have something here. And yeah, and there are a lot of other natural questions which I would like to understand. Maybe the most pressing is, I guess that would be the strongest here, is that assuming that measure hyperfiniteness is not hyperfinite. So maybe you know that the strongest result is possible here, is not hyperfinite, then you automatically have complexity. It seems to be far, but it might be possible, I don't know. But that would be, of course, the nicest thing. And yes, I think, yeah, okay, one more thing. Okay, one more thing I will just finish. So the most important question is, okay, we have all this conditional result, how to construct something which is not which is hyper-hyperfinite but not hyperfinite. Because that would sort of complete the whole study, right? In some sense, we have the sigma 1, 2 completeness result. And the main hardship, again, here is that what appeared before that. We only have measure theoretic tools. Okay, so the question, are there any other kind of tools which can be used in this context? Category is even might be possible to use in a highly non-trivial way. There is this investigation by Guillaume and Filippo recently on Smythe's equivalence relation. I'm a great believer in MZ theory. So, but also there are some limitations to that. So maybe there are some known tools, but I guess the most important question is, can we come up with other tools? That would be also interesting. Okay, thank you for your attention.
Okay, thank you very much. Do we have questions, comments? Okay, let's.
Yes, so I mean, you had your two different worldviews. Is it possible that maybe it's independent which one of them is true, like one under choice, one under determinacy, or something like that?
I mean, I guess it can be always independent, right? But it seems to be unlikely in some sense. But of course, I mean, I'm not suggesting that these worldviews are necessarily sort of exclusive and covering the whole spectrum of possibilities. I mean, it could be something intermediate even. It could be that, I don't know, some measure hyperfinite is not hyperfinite, but I mean, it could be the case that our result is just dumb, right? It could be the case that this collapses, but still somehow this doesn't. So I don't know. I mean, but it seems to be somewhat unlikely. I see a priori no reason why would there be any two classes. Why would they coincide? This is somewhat similar in field to computational complexity. There are a lot of classes, and they very rarely coincide. Maybe we just can't prove that they do. Yeah. Yes.
Okay.
Okay.
Yeah, I have a somewhat maybe basic question, but so you have this nice characterization of hyperfiniteness with these with E0 as a threshold and the group, the orbit equivalence relation. Is there anything like that for hyper-hyperfinite that is known? Is there some kind of group that is universal in the sense that?
Yeah, I mean. So first of all, there are universal equivalence relations for hyper-hyperfiniteness. So there is somebody here in the top. This is because of some abstract results. I think it's Chen and Kekris, if I'm not mistaken, who proved that in a very wide context, you also always have top elements. As for the question whether it can be given by a group action, I would suspect yes, also, but I'm not 100% sure. I mean, issue is that at least this abstract result, it doesn't give you a lot of information. I mean, I can write you in some sense, you just say, okay, we just look at this equivalence relation and we just prove that it's not hyperfinite. That's it. But of course, I mean, if I write down this equivalence relation to you, in some sense, it's just artificially encoded that it's hyper-hyperfinite, and that's it. That's it, and then it doesn't help you in some sense. Yeah.
I just wanted to say just a quick comment on Sandra's question. The union problem cannot be independent. Like if you find a counterexample of hyper-hyperfinite that's not hyperfinite in any extension, there is one in every extension.
Yeah. But forcing, yeah. Yeah, so I mean, even the Riemann hypothesis can be independent, right? So, I mean, but it is true that Schoenfield's absoluteness applies here. So,
any more questions?
Yeah, that's a very good question. I try to figure out it at 7 a.m. in the morning. So this is the reason of this shy, small part here. I guess that it's yes, but I mean, there are some group theoretic operations under which amenable groups should be closed, but I mean, don't take my word for it. I don't.
Okay, so if there are no questions, let's thank Zoltan again.